Welcome back. We'll be looking at 4.2, chapter 4.2 and 4.3 in this video, yeah? So 4.2 covers the energy balance for closed system. Okay, so we're going to look at energy balance for closed system. So from the formula of energy balance, yeah, your thermo 1, first law of thermodynamics, yeah? E in minus E out equals to delta E system. So energy is always conserved. It cannot be destroyed or created, yeah? Nor destroyed, it cannot be destroyed nor created, yeah? So now what we have here is that let's expand what is this E. You know from the previous lessons, or E is what? Your Q, your heat transfer, which is due to the temperature change, right? Remember, when there's a temperature change, there's a drive for heat transfer. And then work. We have got many types of work: mechanical work, electrical work, work because of spring, and so on. And then we have another one, which is the U. U is your internal energy. This is due to the molecular interactions, yeah? So now let's look at the energy balance. E in minus E out equals to delta system. And then we have energy balance from differential form, yeah? And then we have energy balance of a cycle. Energy balance of a cycle is W net out equals to Q net in, yeah? Now let's move on to expanding the formula of Q in, energy in and energy out. Okay, so if you look here, this is for the cycle, still with the cycle, yeah? So it's actually represented by these, just to show you, yeah? First law cannot be proven mathematically, but no process in nature is known to have violated the first law. So this should be taken as a sufficient proof, yeah? Okay, so we are done with the cycle. So cycle, you remember, Q net equals to work net, yeah? Okay, now we're going to move on to the expansion of E in minus E out. E in minus E out equals to delta E. So we have what? You have your Q, you have your W, and then you have your delta U. So this part is the energy part, yeah? Yeah, where you have your KE, your PE. So this one can further expand. Electrical, spring, whatever, yeah? Keep on doing, continuing it, okay? Now, for a constant pressure, for work which is done under constant pressure, how do you get to this formula? Okay, so we're going to look at that. So look at here. So if you look here, we have Q minus work other minus work boundary. So divided the W, yeah, we broke up the W into work other and work boundary. So what is the difference between work other, work boundary? Work other is your work spring, work electricity, or whatever other work, yeah. Work boundary is because of the boundary movement. You see, like this one, you have an object, yeah, a closed system, and then this boundary tend to move. So this is called work boundary. So you take this work boundary and you combine with V. Now where did you get this work boundary? From the work boundary, you see work boundary is P naught V2 minus V1. That is constant pressure, remember? Yeah, for constant pressure cases, yeah, work boundary is this. So now work boundary, you plug in this, yeah, P naught V2 minus V1. Okay. Next, what you do, you expand it, you open it up. Okay, when you open, you shift this one to this side and you open it up, you get this U2 plus P2 V2 minus U1 plus P1 V1. Okay, keep that aside. Now, from the previous lesson, you know that H equals to U plus PV. Remember, I told you the table. Yeah, the steam table. It is actually corresponding to H equals to U plus PV. Now, can you see the U plus PV? You substitute that here. So this becomes H2, this becomes H2, and this becomes H1. So Q minus work other equals to H2 minus H1. So this is the formula. So this formula can be used for quasi-equilibrium constant pressure. Yeah, quasi-equilibrium constant pressure. Based on this formula, we'll be using lots of this formula in chapter 5. Yeah, chapter 5. So for graph representation, when you have a constant pressure, it means it's just a straight line. Okay, from your saturated liquid to your superheated liquid. Yeah, so this case is represented by this graph is represented by this case here, where we have mass 25, pressure is constant, and then because of the electricity, which is work other, you have heating of this substance, this liquid. Okay, so that's done. Okay, And this is an example of a constant pressure. Work electricity in minus with Q out, there is a heat release there, 3.7. Minus with work boundary equals to U, delta U. So you can combine these two, your work boundary, and you open up work on PV, right? We combine with these, you get the H. Okay, so finally work electricity in minus with Q out equals to delta H. Okay, so this is for closed system undergoing a quasi-equilibrium process. This is the same thing. See how they represent it. So now, before we move on to specific heat, I'm just going to explain an example from the back of textbook. Let's look at this example. 4.5 is from your textbook, which is electric heating of a gas at constant pressure. So let's read this question first. A piston cylinder contains 25 grams, not kilograms, grams, so very be careful. Saturated water vapor that is maintained at constant pressure of 300. So how much is pressure? Pressure is 300 kilopascal. A resistance heater within the cylinder is turned on and passes a current. So how much is current going in? Going in at 0.2 ampere for 5 minutes. So all this is current information. You have to plug that out, write it down. At the same time, there is a heat loss, 3.7. So now what you need to do for this question is show that for a closed system, the work boundary and the change in internal energy in the first law of reaction can be combined in the term of delta H. You remember the just now derivation that we did? We just need to prove that. And then your last work is to determine the final temperature. So this part of it is just an explanation. You can just read up by yourself. I'm straight going to the formula. So you always start off with your E in equals to minus E out equals to delta system. From here, expand it. This is the mother formula. So you start expanding it. Q minus work equals to delta U, delta KE, delta PE. So in this question, you don't see that this piston is actually having any velocity. It's not moving. It's not having velocity. There's no velocity. So that is the reason why the KE is positive. And this whole piston is not being elevated up and down. You don't have any elevation of delta H. So that's the reason why your PE is also 0. Okay, leaving you with Q minus work equals to U. You remember the previous formula, we actually break this work into work other with work boundary. Bring your work boundary over this side. So what do you get? You can expand it, and you remember earlier, you expand it and you can cancel it. Okay, leaving you with this formula, which is Q minus work other equals to delta H. Now you need to find what is the work other and what is the other elements that you need to fit in. Okay, work other. Work other in this case, what is entering this piston is only electricity. They didn't talk about any other thing. It's only electricity. So work other would be electricity, where VI delta T, also given in the question. So how much is the work other? 7.2. Keep that aside. So this is settled. And how much is Q? Remember in the Q they said 3.7, isn't it? Went out. Let me just go back, refresh my memory here. You see the loss is 3.7. Okay, so your Q is also settled. Okay, Q is also settled. Okay, now next problem is to find the H. How to find the H? The H. It is a problem. Okay, but in the question they didn't actually ask you the H. They actually ask you for T2. But how do you find the T2? The T2 you have to find from your H2. You go back to your steam table and you have to look. It's like a jigsaw puzzle. It's a chain reaction. Okay, so I'm going to guide you, so you just pay attention. So from the first part of the question, where the pressure is actually 300, we go back, revisit the question. The pressure is 300, given very clearly is saturated water vapor, so you have less headache. So with the 300 and the saturated water vapor, what do? You go to the steam table. Okay, so this is a saturated water pressure table. 1 second, I'm trying to move this. So what is the pressure just now? 300, right? 300. So you need to find, sorry. Undo. How do you undo that? Okay, I'm not going to highlight now. I'm going to just look up here. Okay. So the question is asking you for H value. You need to find the H value. Okay. Now we have 300. Go to the 300. Oh dear, there's so many H value here. Which one do I take? Okay, which one do you take? What does the question say? Saturated liquid or saturated vapor? Revisit the question. It's always okay to revisit the question, yeah? I see. The question say saturated vapor. So you go back to here. So you have to take the 2724 lah. Don't go and take your 561 because this is for saturated liquid, right? Okay. So come back here. You know the value now. Write down the value. See? Just write down the value. Okay, that's settled. So now you have settled this. So what's missing? This is the one that's missing that you're going to look for, right? Okay, plug into the formula. We have work in, we have Q out. Q out, that's why it's negative. Work in is positive. Be careful. Okay, then we have delta H. Delta H is your M multiplied with H and H. Why are you multiplying with mass? Remember, all the values that's in the steam table is actually specific. Yeah, specific divided by kilogram. Can you see that? So that's the reason why your value has to be multiplied by 0.025. Okay, from there you can get your H2. Now your working is not ended here. You take your H2 value, you go back to the steam table. You have to go back to the steam table. The pressure is 300, right? Go back to your steam table. How do you do that? Now it's a bit, so what do? You go to 300, okay? The pressure is constant. So where is the value? Okay, let's check the value. H2 value is 2864. 2864. 2864. 2864. Okay, let's look at this. 2864. Oops. Accident, right? Because the highest value is 2724. It means this table you cannot see. So what do? You go to the steam table. I mean the superheated steam, because it means it is superheated. Okay, it is superheated. So you have to go to 0.3, which is 300 megapascal. Okay, now you look for the H value, the closest H value. Go back. What is the H value? I keep forgetting my H value. What is the H value? 2864. 2864. You go back here. Okay, now you look for 2864. 2864. 2864. Oopsie doopsie. 2864 is actually sitting in between these two values, which means 2864. 2864. Yeah. 2864. 2864 actually is sitting in between which value? We have 0.3 megapascal, 0.3 megapascal, and then we have 2864. 2864. 2864. 2864. Surprisingly, 2864. 0.3. 1 second, I'm just checking the answer. 300 kilopascal is 0.3 megapascal. 0.3 megapascal. Okay, and then the value is 2864. 2864. But they're telling the temperature is 200. Okay. Let me see. Now the final state is completely specified since we know both the pressure and enthalpy. So the temperature at this state is 200. Okay. So strictly speaking, the potential energy changes in steam is not zero, because you see it's a bit tricky. But let me show you why am I myself confused. Okay. Now we have 2864. 2864 is actually in between, not here. It's actually between here. It's between 300 and 400. 2864. 2864. Yes, it's between these two. So how do you interpolate? Your interpolation has to be, okay, this is H, this is temperature, because you need to find your temperature, right? The value that you have is 2864.9, okay, which you don't know. X is the temperature. Okay, and your H value, okay, your H value you take for 300 is 2807. 2807 is 300. Okay, 2807 is 300 degrees C. Okay, and then you have 2966 is for 400. 2966 is for 2966 is for 400. So you need to find the missing X value. Okay, I will not want to maybe this textbook is just trying to find the shortcut. answered, because therefore the steam will be at 200 at the end of the system. Okay, they're just finding. The actual way of doing this is actually from here, where you take this value, you interpolate. Now how to interpolate? Watch this carefully. Yeah, you take this minus this. 2864.9 minus 2807, okay, equivalent to, now you take that minus that, so x minus 300. Okay, next you take this whole thing minus this, 2966 minus 2807 equals to 400 minus 300. So with this you can actually find the value of x. So x would be lying in between somewhere 300 plus. Yeah, press the calculator, you will see that it is 300 plus. So that is the actual temperature value. So the textbook is actually approximating it, yeah, but it's okay. So this is the actual working that you should actually apply. So with that, we are just going to move on to chapter 4.3, which is specific heat. So what is specific heat? In specific heat, we have two types. One is the constant volume and another one is constant pressure. Yeah, energy that is required, it's energy that's required to raise the temperature per unit mass of the substance by 1 degree. Okay, and then we have Cp, which is energy that's raised unit mass of the substance 1 degree as the pressure is maintained constant. Now you remember the line that we drew, this one, you remember this? Okay, Cp is a value that you calculate during this region. This one is called the latent heat. Yeah, it depends on latent heat of fusion or latent heat of vaporization. Fusion is between solid and liquid. Vaporization is between liquid and gas. So now you know where Cp. So this is what we are calculating. Okay. So we have two types, Cp, Cv and Cp. Cv is for volume constant. Cp is for pressure constant. Okay. So how do you find the value of Cp and Cv? Okay. Now, oh yeah, before that, let me just tell you. You see, the energy, you know that the energy is being supplied, right, to heat up the water, example. So in this region, the energy that's used is actually used to increase the temperature. Whereas in the latent heat region, the energy used is actually to break the bonds. So we are now looking at this part. Yeah, energy that is used for raising the temperature. Okay? Okay, that's done. So now let's move on to where do we find. Otherwise this was nothing, it's just explaining to you. Okay, you see here, constant volume and constant pressure specifically, Cv and Cp values for the helium gas. Yes, Cv value is 3.12, Cp value is 5.19. Of course the value will be different because there is a formula behind this. Yeah, I'll show you the formula shortly. Yeah. How come they didn't explain on the formula here? Okay, surprisingly. Okay, this is because this formula, yeah, Cp equals to, wait, I'm just looking for the formula. It is in the next chapter, but I will just show you the formula. Yeah, it's the formula. That's why you see Cp, Cv plus R. Okay, now I'm going to go back here. Yeah, go back here. Now you can understand, right? Why is this C 3.12 and this is 5.19? Yeah. Okay, so that's done. Let me just cover this. Cp is always greater than Cv. Yeah. Yes, because you look at the formula, it makes sense, right? Yeah. Okay, Cv and Cp are properties. Cv is related to changes of internal energy. Yeah. Cv always is related to your internal energy, whereas Cp is always related to your enthalpy. We're coming to that later in the subsequent chapter, but I'll just tell you, show you. Yeah. Okay, what is the thing? A common unit for specific heat is kilojoule per kilogram degree C and kilojoule kilogram K. Are these units identical? Yes, they are, because you see, one rise of Kelvin is actually equivalent to 1 rise of degree C. Of course, Kelvin is like Kelvin is 273 plus with the Celsius, but then one unit of Kelvin rise or drop is actually equivalent to the 1 rise of Celsius drop or increase. Yeah, so that's why it can be compared that way. Okay, so let me see whether I have to cover an example before I let you go. specific heat, or the example comes in chapter 4.4. So I'm going to end the video here. So we're going to continue with this continuation of CP and CV in the next video. Yeah. Okay.